which I'm happy to speak here. And the topic that I chose was in the last 23 years, I'm working on networks, so why not to choose networks? And I want to show you that some examples in which network science can be useful. I know that many of you already showed nice application of networks, but one of my interest is to show you that we have to generalize and to study not only single networks, but to study the interaction between networks. Because networks do not stand alone, they are not isolated, they interact with each other, and this is very important. So, as you can see, I will speak about 4 examples, but there are many, many examples. I did not mention them, but in which we can find useful tools from network to understand what happens, to predict what will happen, and this is, I think, important for the future. And I just give you a summary what happened in the network. Before 2000, network science was called graph theory, and it was built by mostly by Erdos and Reini, 2 mathematicians, very famous. They did a beautiful work, exact work, but they studied Poisson distribution of a degree, which means every node has a typical number of links, and there is a Poisson, a bell-shaped Poisson that describes the degree of distribution, the number of links per node. In 2000, we realized, and this was, I think, a breakthrough in network, realized that networks usually are not Poissonian. They have a broad distribution of degree, and sometimes called scale-free, many real networks, and may be characterized by a power law. The power law is not so critical. What is important is the break of symmetry. Here, there is a symmetry here. Every node, you can see almost the same neighborhood. But when you are here, you see this one sees only 1 node, this green one. But this node sees maybe 100 nodes. So this break of symmetry is very important in physics, because if you have a break of symmetry, you have new laws, new physics laws. And this is what we started in 2000, I think, to understand. So many physical properties are different in this network than this network. And from 2000, we worked a lot on single networks. All the community made a lot of effort. But in 2010, we started to move to network of networks, which we call sometimes multi-layer network, multiplex, but they are all interacting networks. And I am speaking here about specifically about dependency, interdependent networks, which means that no network depends on each other. It means that the links, the red links between the networks are not the same as the black links. And this is very important. The red links are, it means if this node fails, this node will fail also, because this node depends for functionality on this node. And even if it's still connected to the cluster, it fails because it needs some support from other networks. And this is very important because it brings new phenomena that we cannot see in single networks, and I will speak about it. And these are, for example, electrical, communication, transportation, they all depend on each other. And what is important here, I wrote in red, 2 types of links, and brings to novel phenomena that we see now, not only in real world, in the networks that we use to study, but also in physics. And I will show you that we can go from networks to physics back to the lab and create a network of networks in lab, which we did not do before, and see new phenomena that we haven't seen before. So let me start with some examples. Why a network is important for epidemics, sociology. Actually, this is both are social, because epidemics go on social network. I made a friend and I infect him. And so it means this is social, and this is like technology. So I gave you 2 examples of social, 2 examples of technology, and you can find in literature many, many papers on other systems in which network is useful. So let me start with, again, this one, okay. No, also this one doesn't work. See, there's always, okay, now it works. Let me see, okay, it works good. So let me show you what we can study in using network for epidemics or for COVID. And actually, there was a big article on this in New York Times about how to change the policy of immunization. So what we see here is a network, and usually we supply the units of immunization units randomly to the people. But now if we don't supply to the people that we want, but we ask them, give me a name of your friend, and you supply to him, instead of needing that you need 100% of to immunize 100% of the people, you will need only 20-25% of the people. It means we know the structure of the network, we don't need to immunize 100% of the people, but if you immunize friends of some people, just choose randomly some person and tell him, give me a name of your friend, immunize them, and then it reduces by a factor of 4. Not only this, so the QC, you see, QC means the fraction that you need to immunize. Lambda means this parameter. Usually in social network, we are in this range of lambda. And in this range of lambda, you need 100% randomly. But if you choose acquaintance immunization, what you call here, it means it reduces the fraction that you need to immunize by a factor of 4. And the same we show in another paper, which is this paper. This was during the COVID, that, it was not convenient to ask person, but if you choose, for example, a group of 5 to 10 people, and you say, okay, I choose from these 10 people, from these 5 people, the most connected person, I go to for a company and ask them, who is the most connected people, and immunize them, it also reduces by a factor of 3 or 4. It means you can do tricks in order to use less immunization unit or quarantine, the same. So instead of using, for example, if I take the highest degree node, this is the best one to immunize. You see, this is the lowest, it's about 10%. But if I choose now, I choose 3 people, and I say, okay, this one has only 1 friend, this one has 3, and this one has 4, let's immunize this, then it also reduces by a factor of 3 or 4. So it means you can use the network in order to make efficient immunization. So this is one example, the social network in which you can immunize properly a community by much less vaccines. Now, another paper that we did was published 2 years ago. It's by a Chinese person who works with me, Zeng. And the question is, what happens? Can we improve our scientific output? Improve means like having more original papers or more multidisciplinary papers. And we found that if you take fresh team, I mean people that did not collaborate before as much as possible, then your chance to have a paper which is more original and more multidisciplinary is higher. And what is meaning, so we look on the authors of the paper, of this paper, and we see that these authors already published before. This one published this paper with this one. This one published this paper with this one. So it means the team freshness is very low, close to 0 here. But here, all the 4 published this paper, but nobody published earlier papers together. It means the team freshness is higher. And actually, we looked also the team freshness. We see that there are about 40% of people, 2 authors, they are not fresh, and the fresh is more. And here we see how many you have fresh in different 4 author paper, how many you have. And you can see that there are many people that indeed have a fresh team, and the fresh team has a chance to have a much higher original paper. We call it disruption paper. And we have a method. There are several methods to find what is a disruption paper. For example, disruption paper, it means that people that cite this paper don't cite papers that were cited in the same paper. It means they cite this paper, but not other. Or multidisciplinary, it means that the people that cite this paper, they cite not non-overlapping references. It means like multidisciplinary. And we can see it's systematic. We checked it very carefully for two authors' paper. You see that the disruption, it means the originality is higher, the multidisciplinary is higher for 4, and for 8 even auto, you see systematically increase in this. So it means it's better to work a fresh team, because everyone brings their own idea and something comes out which is much more original and more multidisciplinary. Now I come to traffic, and this deserves a little more attention because traffic is really a big problem. And I want to show you that network science, and in particular percolation theory, can be very useful for improving traffic. So let me show you this example. This is actually the first paper where we used the percolation in 2015. We took China, a part of China, and we made it like a network. It means the link is like a road here, and the junction and the node is a junction. And this junction has, for example, 3 roads. This junction has only, this one is 3 also. So we made a network because they are connected. And we look on the speed on each road during the day, every minute. They have information about the speed in each road or every minute. So good speed will be like green, medium speed will be yellow, and bad speed, it means very slow, like jump, will be red. And this is what we did. And we had not only good, bad, and medium, but we had exactly the speed in each minute of each road. When we do this, we looked on a parameter that we invented, is the threshold. Actually, it was mentioned by you also. We look at the threshold. If I allow, and I don't care about the threshold of the speed. This is like the fraction, the speed, relative speed in the road during the day. If I don't care, then all the cluster is connected. This is the cluster, means I can go from everywhere to everywhere. If I don't care about the speed, very slow, I can go also. Now, if I increase a little the speed, I cannot go everywhere. You see, this, it goes down. The component where I can can drive becomes smaller, but it drops dramatically. And the second largest component that I can drive makes a big peak. And this is typical for percolation. And what we realized that the QC where it drops, which means what is the fraction of the speed that the system starts to be above which I cannot move, below which I can move in the system on all cluster almost, but above this threshold I can move, is changing during the day in such a way which is clear, and during the night, this is during the night, QC is large, then becomes smaller during 7 o'clock in the morning, and then it becomes much smaller. You see here, this is the work days, and this is the days off, the green one, and you see the 2 peaks here. It means, and we found now that this is a characteristic of a city. Each city has its own graph like this, and we are going to publish a paper about this. We measure many cities, and the cities are very similar. In the same city, it's very similar every day, this graph. It means it's like a critical threshold. But now, what is important, imagine that I watch this curve in the control of the city, and I see, boom, it jumps from the curve. It means I know I have a big problem in the city. And this is why Chinese companies are interested, and they start to put it in their control system to check it. So it means you have a percolation process that the system breaks down at a certain critical velocity. What is more interesting is that we found the position that they break, because it becomes, instead of being one cluster, it becomes several clusters. So we look on the position, the bottlenecks, where the cars cannot move in the velocity, and we see that the bottlenecks are typical. In the morning, they are the same. You see, this is the morning. This is the seven most frequent typical bottlenecks. In the evening, they are the blue one. But during lunchtime, all of them appear. You see blue, green, and red. It means you can even see that there is some systematic in the system in which you can identify which are the bottlenecks of the city that doesn't allow us to go from neighborhood to neighborhood, which are bottlenecks that they make the system break down. Now, new work that we are working together with in a European project together with Dirk and others, and we study how to predict jumps. And this is a paper that is going to be soon in the press. I hope it's under review now. It's to predict jumps in a city. It's important. I'm sorry, here it's a mistake. And improving flow via controlling lights, and to use lights in order to improve the flow of the system. And the way we do it, we found surprisingly that if I make a jump tree means that I look the one that congested the earlier one. This was congested before 12 units of time. This was 12 units of time. This is all 12. This is 11. So I call, and this is 10. And I'm sorry, 10, this 10 is not related, but this is 10. So this one is like a jump tree. Now, there is another jump tree here. You see, they may be connected, but this jump tree, because it goes in the other direction, so I can see this is a jump tree that starts from here to here. This can be associated to this one and to this one, because people can go direct and can go to the right. And this is another jump tree. So when we look on the jump trees, we see that the jump trees increases, usually this is typical way of jump tree, it increases very fast. They become congested very fast, jump tree, and dilute very, very slow. Usually the factor is about time, factor of time is about 2, mostly 2. I mean, the most probably 2 times is recovered with respect to the time that it becomes maximal size. And now we looked and we found that there is strong correlation between the time that of the speed of the beginning of the growth, the speed that it becomes congested in first 5, 10, 15 minutes, with the size, the maximum size of the jump tree. It means from the beginning, which I can measure in the first 5 minutes, and the first 10 minutes, I can see a jump start to create. I can tell you with high probability what will be the size of the jump. The more speed it is, the more it is. And this is the correlation you see between the speed, the initial speed, and the jump. And it means for 5, I have a correlation which is about 0.7, depending on it is. But when I go to 15 minutes, I already know it's high probability what will be. And this is the rock curves that tells us in 2 cities that we can really have a good prediction for big jumps during, if we look on the beginning of the jump. Beginning, we start to be a jump to see how fast it becomes in the first 5, 10, 15 minutes, and you have a very strong correlation. This is 2 cities, and then we ask ourselves, this is another paper which is already in archive. I'm giving you results that are not published yet. We looked how we can use this information in order to improve the lights and in order to improve the traffic. And we find that if I look on I make the lights, for example, in this, I see the lights that comes, I see the amount of traffic that comes from here, the amount of traffic comes from here, the amount of traffic comes from here, and I see the jump tree that this link has behind him. It means it's not only the next one. I look on all the tree that is followed it, and I can estimate in a given time what is the jump tree, and I can make the lights, actually, usually the lights are maybe 90 seconds, so I can share the lights according to the size of the tree that every link has in the system. And this improves by, I didn't write it here, but improved by 30–40% the current most efficient system. So we compared it to other systems, and we see that by looking on the jump tree, we can improve this. Now, okay, so this is the traffic jump. So it means that using percolation, using network theory, you can improve traffic jams, improve, yeah. Now, why do we need a network of networks? So this is the example where we see in Japan, in Tokyo, you see cascading disaster in Japan. It means that, the power grid was infected by the earthquake, and then all other systems, other infrastructure like transportation, communication, everything was connected to the power grid. So it means if the power grid doesn't work, it means all the others also. So this is what is described in this war. And in the same day, I gave a talk in Boston, and I saw in the hotel this paper, so I made a photo and showed it to the audience to try to convince them why we need network of networks. And indeed, it's not my invention that we need it. This was already by Rinaldi, an engineer from Italy, I think from Florence, who wrote how interdependent are infrastructures. But we didn't have a tool to study this mathematically or in other way. So you see the power grid is not alone. It depends on many other systems. Everyone depends on each other. So it means you need a system of systems. And indeed, also in 2003, it was documented by Rosato, also engineer from, I think, from Florence also, that the blackout in Italy was caused by interaction between the power grid and the communication of the power, the SCADA that controls the power grid. Failures here led to failures here and backfire, and this led to a breakdown of the system, and they had to stop the power grid in all Italy, not only in Italy, it was also part of Switzerland also. So here we came in 2009, in 2010, actually the paper in 2010, with a model in which the simplest model to study interdependent networks. So this is what we studied, one single network. Now we assume that this network is part of a network of network. So each node is a network. You see, this is a network, this is a network, this one, and these links tell you which network depends on which one. For example, this one depends on this one, and vice versa, and this one depends on this one, vice versa. Now, the vice versa is not essential. Even if it's one direction, the results are very similar. But now we found that if you take 5 networks, n equal 5, or any number of n, and I put them in any tree structure, any type of tree without loops, I get a formula which tells you analytically exactly what is the giant component that is left when I keep only p, a fraction of p of nodes, 1 minus p, I remove randomly from this network of networks, and what is the giant component that is left. And if I compare this to the result that was found now 64 years ago by Erdos and Raimi for a single network, this was the result. And when I compare this and this, there is no much difference. Only there is a small n here, which makes the difference instead of being no n here, because Erdos did not study interdependent network, he studied single network. Of course, if you put here n equal 1, it will make this the same result that was before, and it's continuous solution. But when you go to n equal 2, you start to have a new process, which was not before. It means cascading failure between the networks. It means if I have here failures here, it leads to failures here because of the red links. It leads to failures here, and back to failure. This cascading did not appear in the general theory of network, and now we have it. And look how similar it is to this formula. When I put n equal 1, I see a continuous solution. It means that when p is 1, everyone is connected. Everyone can send the email to everyone, and p infinity is 1. P infinity is the fraction of the giant component here, and everyone. But when I start to remove, only if I remove 80% of these nodes, it breaks down. But when I have now network of network, let's say n equal 2 networks, I see also a part continuously, but when I reach a point, then enough damage was made in the system, and this damage makes spontaneously more damage in the system because of the dependency, and the system falls dramatically down here. So it means the generalization is very natural for this system. And now what can we learn from this? I think we can learn a lot. This is only one example that it becomes abrupt instead of continuous. But this abrupt, when we look on it carefully, this is a single network. This is called a second order continuous transition. This is coupled networks. Then we see abrupt, which we call first order because the jump is first order. We looked on what happens in this jump. Because if we have analytical solution, and you remember this is analytical solution, we can see the process in which we reach this formula. We look on steps in the process, and we can identify exactly what happens here. And what we see here, this is the jump here, you see, and I look on this jump, and I look how it evolves with iterations. It means because I have two networks, so failures here lead to failures here, and back and forth, these failures, and I see that you have a plateau like this. It doesn't fall abruptly like this. It falls abruptly when you change P. But when you keep P here, PC, and you look on the system, it starts to evolve spontaneously because failures lead to failures in the other one, back failures here, and you see a plateau. And this plateau, I tell you, is very general. It appears more and more. I can see in more systems. When you have such a transition, it's not just a jump. Usually it's a plateau. And this plateau has a very deep concept. What happens in this plateau? In this plateau, microscopic interaction between the two systems appear only. Microscopic, it means a small scale. Few nodes here, 1 or 2 or 3 made damage here, and few nodes here make damage here. That's why it's a plateau. It does not drop dramatically. It's a very small. And indeed, when we take a larger system, because it's microscopic, this plateau becomes longer and longer and longer and approach to infinite. And this is a tau of the plateau, and we also predict this. This is already done in 14, and now we see it in many systems. So we expect that to see this also in other systems. So the question is, I came from physics in 2000 from physics to network, and all the time bothered me, what can I do for physics? Can I come back to physics? Can I learn from network science to physics? And then I asked my question, can we realize and prove the theory of interdependent network in controlled physical systems? Because worldwide systems like internet traffic, I cannot control. Nobody allows me to change anything in the internet or in the power grid or traffic even. I cannot. But then I wanted to do physics experiment and to see what happens. And indeed, in the physics experiment, we took 2 layers. Each layer is one network, which is a superconducting network. It means in low temperature, it is superconducting. In high temperature, it is conducting. It becomes not superconducting. And the same the other layer. And we couple them by dependency links. The dependency here is thermal conductor between them. It means it's not, we don't have any current going from between one system to the other. Only heat can go from. And my idea was that if I do this, it will be like dependency, because if somebody becomes some superconductor become conductor, it will become heat, become hot, and this heat will go to the other one and make the other one also like dependency. I control one, will control the other. And indeed, when we measure, and luckily I had one, and luckily because the experimentalist was in my building, just I had to go 2 floors down to find him, but I bothered him since 2011. He tried and he tried, and only in 2022, 11 years, he succeeded to do the experiment. So the experiment you see is in a single network. You take single one, you see continuous transition. This is the experiment, and this is the theory. We use Kirchhoff equation, we use Josephson junction, and we find the theory. Now, what happens when I couple them to make dependence? It means dependence means I put a layer in between, which does not conduct electricity, like in the interdependent. I cannot move in the interdependent network. I could not move from one network to another, but they depend on each other. So here the dependency is the heat can go from one layer to another, and I wanted to see what happens. So indeed, we put them together. In between, there is a layer which is conducting thermal conductance, but electric isolator. It means only heat can go. And look what happens to the result, the single network results, which were continuous. They become abrupt here. Not only abrupt, you see, this is the top one, this is the bottom one. The bottom one, not only abrupt, we see also hysteresis. Usually when you have abrupt transition in physics, you have hysteresis. And not only this, we can see very nice the plateau. You remember I told you, we have a plateau. We have a plateau. This plateau. You see this plateau? We predicted even the plateau with dependency. And we have also a plateau here. The plateau here, you see, each one does not jump from here to here or from here to here. It jumps to a state in the middle, and then it jumps. And this time is time of seconds. You can measure it in the lab. And not only this, you can see that if you are going far from the critical point, it becomes shorter and shorter and shorter. This is close to the critical point. So the experiment, we did not publish yet this, but I'm telling you that we see beautiful results like interdependent abstract networks of percolation theory. So it means that we have now a system in which we can control. We can control the dependency, we can control the current, we can control the heat, and we can see what will happen in the future. So let me summarize. I think it's time. So I told you that network science can promise social innovation. I showed you efficient immunization. I know the network. If I know all the network, then I can do the best. I immunize only the hubs, and I need only 10% of the people to immunize. But if I don't know, I still can use acquaintance immunization or choose a group of people and ask who is the most connected one and immunize them. So this is the first one. Second, I showed you that originality of a paper and multidisciplinary increase in fresh teams. Fresh teams are very important to bring ideas which, because if two people worked before, this usually produce similar things that they did before, but usually this one is more, and you can see it here also. Yeah, this is the figure. Now, forecasting traffic jams. I told you, I think it's a good method to make the jump trees for the system, and the jam you see is fast going up, but slow going down. I told you, typically it's a factor of two times recovery compared to the time of growth, and the speed in the beginning tells you how big is the jump. This is, I think, surprising. It tells you 95% accurate jump. So, and this can be used in order to improve traffic. It means if I give priorities in the light, according to the jump tree that this road hold. You see, each road has and I know this information because I know the speed of the road every time, so I can estimate what is the size of the jump tree that goes one after the other. And if I give according to this, I split the 90 seconds, for example, round into this. And then we did experiments, we did simulation in this paper I showed you before. It's a Xerox paper, and we find. But the most interesting part is the interdependent infrastructures that we can see abrupt collapse instead of continuous in single one. And more than that, we see that there is interaction between the two systems, which are microscopically. You have two macroscopic systems, and I believe this is will appear in many systems. Even our body, maybe, I don't know, I hope we can see it, that there is a stage in which you have a small, there is a collapse of the system, but before the collapse, I hope we can see the plateau that it's a microscopic interaction. And this plateau is also very important because during the plateau, maybe we have time to change things. The plateau, in this case, is second. Thousands can be 1,000 seconds, depends on the size of the system. The bigger is the size, the more time it takes, because it's microscopic. It needs to make many changes in the systems. But it's microscopic. It's not only this. It's also the branching factor is one. This is very important. It means during this jump, the branching factor is one. But we know branching factor 1 is critical. So we found the branching factor here. This is 1. It means why it is a plateau, because it's a small amount, but the small amount does not bring a bigger amount in the other layer. It brings the same size, and it brings the same size here. So this is like the critical. So we can understand why we have such abrupt transition and what happens microscopically in this abrupt transition. Thank you very much.